As we discussed in the previous video clip, the ideal Brayton cycle consists of 4 components. The first one is compressor, and we have heat exchanger where we have heat input, and we have turbine, and we have heat exchanger that rejects heat to the outside. So each component and each process should be idealized because we are going to talk about the ideal Brayton cycle. So when you think about these ideal processes for each component, we can make 4 basic processes. The first process is reversible adiabatic compression process. And the reversible adiabatic process can be considered to be isentropic. So the first process is isentropic compression. Then after compressor, we have a heat addition process, which is considered to be constant pressure heat addition process. Then the next process is isentropic expansion in a turbine. Then we have again constant pressure heat rejection process. Then we have to focus on these 2 heat addition and heat rejection processes. Then why can we consider those heat addition and heat rejection process to be constant pressure processes? So in order to understand these 2, we have to really think about how we can assume this entire gas turbine processes. Is it a closed system analysis or is it open system analysis? I hope that you now can recall what we discussed for Otto cycle analysis and diesel cycle analysis. So in those types of reciprocating engines, we basically think about this whole process as air compressed and expanded inside piston and cylinder assembly. So because of that, we assume that entire compression and entire process or system itself to be a closed system. But when you really think about how this gas turbine is operated, then we basically can see the air keeps flowing through each component. So what I mean by it is that each component can be or should be considered to be an open system. So now the basic idea of doing the thermodynamic cycle analysis for the ideal Brayton cycle is based upon the fact that all components should be analyzed in terms of open system. Now, because we are talking about very ideal conditions for open system, now when we have certain flow inside the component, we basically assume that there should be no pressure decrease due to friction. So that's why we can assume that even in the inside heat transfer, heat addition and heat rejection processes in both heat exchanger, we can assume that those are under the constant pressure flowing condition. So that is why we consider those heat addition and heat rejection process to be under constant pressure processes. And that is the biggest difference. Now, with those 4 processes, can you draw the TS diagram and PV diagram? For TS diagram, the isentropic compression process can be drawn as a vertical line going up from 1 to 2, right? Okay, because we have compression and usually a high pressure curve goes up in the TS diagram. And now from 2 to 3, we have constant pressure heat addition process. And I now hope that you remember why we draw the constant pressure process this way in the TS diagram. And now from the 3 to 4, we have isentropic expansion process, okay, which is also vertical line, but going down from 3 to 4. Then from 4 to 1, that is constant pressure heat rejection process. So we can draw the TS diagram from 1 throughout 4 this way, okay. Then during the process from 2 to 3, we have heat in, okay, and from 4 to 1 process, we have heat rejection. Now, how can you graphically represent the net work in the TS diagram? Yes, the net amount of work can be represented by the area surrounded by those four processes. That is how we can understand the amount of net work graphically. Then how about PV diagram? Okay, from 1 to 2, still there is isentropic compression process. So it should follow that kind of curve. Okay, I hope that you also remember why we can draw the line of compression, the isentropic compression process this way in the PV diagram, which is quite the same as the way that we draw PV diagram in the Otto cycle or Digia cycle. Now, during the process 2 to 3, it should be a horizontal line because that should be a constant pressure process. And 3 to 4, we also follow that kind of curve, which is the isentropic expansion process. And from 4 to 1, then we have constant pressure process again. Also, the net amount of work in the PV diagram can be represented by the area surrounded by these four processes. Honestly speaking, when you deal with the ideal Brayton cycle, we don't much care about the PV diagram anymore. But instead, we care much more about the TS diagram, because the TS diagram gives us more information and graphically that is more clear. Okay? So, I'm going to use the TS diagram a lot for the ideal Brayton cycle analysis. And I hope you also should be able to draw the TS diagram for the ideal Brayton cycle. Okay, so by looking at this TS diagram again, we have to really discuss the key design parameter for the ideal Brayton cycle. I hope you can remember what were the key design parameters when you talked about the Otto cycle and Digia cycle. For the Otto cycle, we talked about the compression ratio as the key design parameter. Okay? And for the Digia cycle, we had two key design parameters, which are compression ratio and the cutoff ratio. But in these both engines, the compression ratio is very important because piston moves up and down to compress the air in terms of its volume from the biggest volume to smallest volume. So that's why the compression ratio is very important. But when you go back to the Brayton cycle or gas turbine, what matters is not about the volume change, because that is a kind of continuous flowing condition. What you have to look at is how the pressure is increased in the compression process. So the key design parameters in the gas turbine is how pressure changes from the low, almost same as the atmospheric pressure, to the higher pressure as a result of compression. And we call that design parameter as pressure ratio. Okay, and I'm going to use R sub P, which is defined as the pressure at the end of compression to the pressure before the compression. And that is the most important design parameter for the gas turbine. Now, again, when you think about the thermodynamic analysis of a thermodynamic cycle, we always have to think about two factors. One is the net amount of work, and second one is the thermal efficiency. Even for the Brayton cycle, the net amount of work should be calculated by comparing heat input and heat output. Okay? Or we can calculate the same thing from the expansion work or turbine work that is occurring at the turbine minus compression work that happens in the compressor. So either equation is used, it doesn't really matter because we should get the same value. Sometimes we use the net amount of work per unit mass, which also can be related with small q in minus small q out. and heat input and heat output per unit mass, or turbine work minus compressor work per unit mass as well. Okay. And now the second thing that we have to think about is thermal efficiency, which is defined as net amount of work divided by heat input, or which is the same as in capital case as well.